Hey, what's up guys? So I'm here to make a video on an introduction to polar form. So traditionally, when we've been thinking about plotting a point or a graph, we usually use it in terms of x and y. And we do that, the x represents a horizontal component and the y represents a vertical component. But it turns out there's another way that you can represent points that we're going to also use sometimes because it turns out to be a lot more convenient from time to time. That's by measuring in terms of r and theta. So you're going to think of r as being some kind of distance from the origin. And we're going to think of theta as just the angle from the positive x-axis. In the same way that we always measure angles with, like here's 0, here's pi over 2, here's pi, and so forth. Okay. So we're going to start today by talking about points and then move on to graphs. And in the next video, I'll talk about calculus. So suppose we have the point here, 3 comma pi over 6. Now, we're going to see this is a different graph. Now, when we think about this, we still have like the y on top and the x is side to side. But I'm going to give you the point in this r theta form. And what we see around the graph is we see here's the origin at 0, 0, but then we have different angles. So the thetas are the angles that are measured along here like we're used to, and then each kind of circle outwards is one r. So the first circle is like r equals 1, and then r equals 2, r equals 3, r equals 4, and so forth. So that's how we're going to kind of represent points in here. All right, so let's say we plot the point 3 pi over 6. The first thing you want to do is go out to the angles. You say, okay, I'm going to go out to the angle pi over 6, so there's my angle, and then I'm going to go out 1, 2, 3 units along there. So right there, that red dot, that's the point 3 comma pi over 6. So we're representing that, again, notice like, okay, I just kind of went out to the angle pi over 6, and then I marched out 3 units from there to get to that point. Okay, so what if we have the point 4 comma pi over 2? So that's the next one. So this is saying let's first go to the angle pi over 2, which of course is up here, and let's go out 1, 2, 3, 4. Okay, so that's the point that we did. So that's the point 4 comma pi over 2. And I might ask you, like, what is this in Cartesian coordinates or rectangular coordinates? That's just the x and y, and that's just saying that's the point 0 comma 4. So we could talk about this point as saying like it has a horizontal component of 0, vertical component of 4, or we could say it has an angle pi over 2 and then a distance of 4 units. So again, think of that r as like a distance from the origin. Okay, now the cool thing about this, or maybe it's cool, is you can actually have a negative r and a negative theta. So here, when you have a negative r value, what your thought should be is to go away from the angle instead of towards it. So if you have negative 3 comma 7 pi over 6, so that's saying, okay, you go out here, let's pick another color, so you go out here to 7 pi over 6. But instead of going towards it on that line, you're going to go back away from it 1, 2, 3 points. Oh, it's also the same point. So that same point there could also be referred to as negative 3 comma 7 pi over 6. So that's just another way that you can represent things. So you could go out to pi over 6 and go out 3 units, or you could go around 7 pi over 6 and go backwards, that's that negative 3 units. Okay, and then if you have a negative angle here, then that would be, let's choose yet again another color. If you have a negative angle, of course that just means go backwards until you get to the angle. So if you have like negative pi over 3, it's just saying, okay, I'm going to go backwards pi over 3 units. So 5 pi over 3 is in the same spot as negative pi over 3, and then I'm going to go out, because usually we measure in the counterclockwise direction, but if we have a negative angle, we go backwards, and now we just go out 1, 2, 3 units to that point. So that's how you deal with like a negative radius, which goes backwards, or a negative angle where you just measure the angle backwards. Okay, so let's talk about some other ways that you can write the point 4 comma 3 pi over 2. So let's think about like what this represents. And again, this is something that makes polar a little confusing from time to time, is you can represent a point in different ways. So when we have 4 3 pi over 2, that's saying, okay, let's go around to 3 pi over 2, because here's pi, here's 3 pi over 2, and then let's go out 4 to that point. Now, you could also write this as saying, okay, well, instead of going to 3 pi over 2, what if I just went backwards the other direction? So what if I went to like negative pi over 2 and then I went out 4 units? Or maybe I just went to pi over 2, but then instead of going positive 4, I went negative 4 away from pi over 2. And if you plot those points, you'll see those are just different ways to represent that point. And of course, in xy form, this is just the point 0 comma 4. There's only really one way to write that. So that's what's going on here. We're just trying to represent points in a different fashion with r and theta instead, and that distance from the origin for r and the angle theta instead of horizontal and vertical. Now, one thing I want to talk about is that graphs look a lot different. And when we see a graph in normal function mode, it may not look anything like the graph in polar mode. So for example, let's say you have y equals 2 plus 2 sine x. You can graph this in your calculator or whatever, and it looks like this. You go up. Like that's what the graph looks like. Now, if you were to graph this now in polar mode, so in polar, we're graphing r equals 2 plus 2 sine theta. The theta is kind of analogous to x. That's the value you plug in, right? Because you have r equals just the same way you have y equals. So you plug in theta values and get a value for r. So if you plug these in, you plug in 0, you get 2 plus 2 sine of 0, which is, let's see, 2 plus 0, so that's just 2. So what I'm going to do is I'm going to get a table and draw a picture so we can kind of see what this polar graph looks like. Okay, so pi over 4, let's say we have 2 plus 2 sine of pi over 4. Well, that ends up being, 2 plus root 2, which is like roughly 3.4. That's a pretty rough estimate. Okay, and then pi over 2, we do 2 plus 2 sine pi over 2. Okay, and the sine of pi over 2, of course, is 1, so that just ends up being 4. I'll skip some time here. So 3.4, and then this goes to 2, and then here we end up getting like roughly, well, we get 2 minus root 2, and then we get 0, and then 2 minus root 2, and then we get back to 2. Anyway, so let's go ahead and plot these points. So when you start at the point 0, 2, so you go to 0 and then go out to 2. And then here's pi over 4, of course, halfway between pi over 6, pi over 3. So we go out about 3.4. So 1, 2, 3, and change, somewhere around there. And then you go up to 4 here. And then you have like roughly 3.4 in there. And then you go back to 2. So if we're trying to draw the graph, it kind of goes in a circle. So we like connect in order. So we start at 0, and we kind of connect in counterclockwise order as we go around the graph. Okay, now let's keep going. When we plug in the pi, we got 2 and then 2 minus root 2, so that's like roughly 0.6. It's a little less than that, but whatever. So then you're at like a little bit in there. And then at 3 pi over 2, 0, then you actually get back to the origin. So the graph kind of goes like that. And then you have, again, a 0.6 out here. And then you get back over to this point. So that's roughly what the graph looks like. So it makes this weird kind of like a heart kind of shape in a sense where it goes around like that. And again, I just graphed a couple points, but that's the general shape. Okay, so that's how you make a polar graph. You kind of plug in the thetas, you plot the points, and then you connect counterclockwise. Now, realistically, drawing one of these is not something you'll ever have to do on the AP test. I just want to show you what's happening when you see a graph or when your calculator graphs something. So I'll show you how to graph this in your calculator. So let's go to your calculator. Here's my ghetto app. So if you go to mode, one of the options, I know mine looks a little different, one of the options down here under function, instead of par, you can put it in polar mode. So go ahead and hit that and go back to your main screen. Now when you go to y equals, you'll see it's r equals something. And now you're going to do 2 plus, let's just graph the one we just did, 2 plus 2 sine of theta. Just hit the X button. And then when you graph this, okay, this is what it's going to look like. And I need to, oh, my window is god-awful. Okay, so there we go. So that's what my window looks like right there. So I'm just going, it just shows me the X and the Y, but we see it has that same kind of upside down heart shape. Now, when you go to your window settings, that like theta min and theta max, that's like the T min and T max in your parametric. It'll just graph the angles between 0 and 2 pi, and that's pretty much what we always want to see. Anyway, so that's how you graph those on your calculator. Let's talk about converting. So if you have an X and a Y, how do you get to an R and a theta, or vice versa? So if you have some point, let's just call the point here X, Y. You could go out to the point by going X units over to the side and then Y units up. Now, when we think about R is the distance from the origin. So R is just that straight line distance, and of course that turns out to be the hypotenuse of the triangle. Okay, now, if you want to combine, make some way to solve for X and Y in terms of R and theta, theta of course is the angle from the X axis. So let's do some trick. The cosine of that angle would be adjacent over hypotenuse, so the cosine would be X over R. So if you wanted to solve for X, you just multiply by R on both sides, and X equals R times the cosine of theta. Now the sine of the angle, of course, that's opposite over adjacent, so Y over R, so multiply by R, so Y is equal to R times the sine of theta. put a huge box around these equations. This is how, if you have r and theta, you can put it back in terms of x and y, and this turns out to be crucial. Okay, so if I just give you a point, like I give you the r and the theta there, you can find the x and the y pretty easily. So if this is my r, this is my theta, my x is just 3 times cosine of pi over 6. The cosine of pi over 6 is just root 3 over 2. So that's 3 rad 3 over 2. The y is 3 sine of pi over 6, which turns out to just be 3/2. Okay, so that's how, if you're given an r and a theta, how you can get the x and the y points to get the horizontal and vertical components. You can do this if you have equations as well. So if you have y equals 3x plus 2, you can actually use these equations and plug them in. So I could take them and plug them into the y and plug them into the x. So I'm going to get r sine of theta equals 3 times r cosine theta plus 2. Now, when you put something in polar form, just like regular form, we want to have a y equals. In polar form, you want to have an r equals. So I'm going to just get everything to one side here. So r sine theta minus 3r cosine theta equals 2. Factor in r, and I'm left with sine theta minus 3 cosine of theta equals 2. So that means my r is 2 divided by the sine of theta minus 3 cosine of theta. Okay, so that's how I can solve for the r and figure it out that way. Okay, cool. So that's how you take an x and a y and you put it in polar form. What if you get the other way? What if you have the x and the y and you're trying to solve for what r is and what theta is? Now you can kind of work backwards on this. And these equations are not as useful as like these box equations we use all the time. But if you know what x and y are, well, and you want to find like what does r equal in terms of x and y, what does theta equal in terms of x and y, that problem is not actually too bad, right? If we want to solve for r, this is a right triangle, so we can say x squared plus y squared equals r squared. So r turns out to just be the square root of x squared plus y squared. All right, if you want to solve for theta and you have x and y, that's a little more complicated here. But if we want to set this up, like the tangent of theta equals y over x, like that's an equation that involves theta, x, and y. So you could write theta as the inverse tangent of y over x. Now, again, these equations we're not going to use a ton in this class, but it's nice to know if you have y and x, here's how you can get the r and the theta. Most of the time when we're converting, we're going to use this equation. But again, the main things in today were these equations for x and y, but then also like what it means to graph a polar function and what it means to graph points in polar form and what that represents. Okay, now the only other thing I want you to do from this video, go to your calculator and graph r equals 4 sine 4 theta and r equals 3 tangent 2 theta, and you're going to find out that polar curves can be beautiful. All right, I'll see you in the next video. Thanks for watching.